with Mauricio del Razo, who's in SUSE Institute and FU Berlin, and he will talk about the entropy production of reaction diffusion process.
Okay, so cool guys, thanks for having me. So it's really nice to be back. And I think I was just talking to Tuan, and I realized that I think I gave one of the first ones, if not the first one, deep seminar given by a deep fellow. So that was some time ago. So it's really nice to, and then I didn't give any other one. So it's nice to be back and give another talk here. Yeah, so today I want to tell you about this entropy production of reaction diffusion processes with applications to enzyme kinetics. So there's some parts of the talk that might be a bit technical, but I'll try to make it like easy to follow and explain the topic. So you bear with me. I hope I can explain it well. And it has 3 parts or 4 parts. So if you get lost in one, try to connect again in the next one, and then it should maybe work out well. So okay, this collaboration with Artemi Kolczynski in the Pompeu Fabra University and Suzuki Ito. So it's a joint work, and maybe I can start with like, why am I interested in reaction diffusion process? So you think about biochemical process in living cells, they involve a lot of molecules, right? So here you can see all of these are different molecules interacting with each other. It's quite a complex system. The relevance of biological process in the scale of seconds. So it's basically impossible to do it at the molecular level, right? We can barely do the interaction between 2 molecules in a small box for some milliseconds. And so trying to do the scale of such a system is ridiculous. But we can try to come up with a coarse-grained model. However, this coarse-grained model perhaps will not have the right parameters, right? Because in principle, we need to parameterize it with such simulations. So with this in mind, I just want to say, like, the aim of the talk is not to give you some quantitative understanding of the system or something that you can really calculate with like numbers. I mean, there's a part that you can do something with numbers, but the idea is actually to get a qualitative understanding or improve the qualitative understanding of biochemical processes. So how do things work? In which kind of settings can such things happen, right? So this is a bit the idea of the talk. And with this in mind, then we can use the reaction diffusion models to try to see how biochemical processes work. Okay, so when I talk about a reaction diffusion process at the particle level, what I mean is, okay, I can coarse grain a molecule, one of these big things that you saw before, as this sphere, like A, and then another molecule as a B. And then these molecules are immersed in a solvent, so they follow Brownian motion. And if they get close to each other, close enough, they might react and become another molecule, right? So there's a chemical reaction happening. So the idea, this is the very basic idea of a reaction diffusion process at the particle level. And what I'm going to do in this talk is combine this with the stochastic thermodynamics to try to gain some insight on how these systems work. Okay, so with this, I do the outline of the talk. So to understand a bit what stochastic thermodynamics is, I'm going to start with an intuitive approach to stochastic entropy. Then I'm going to go and show you how can one obtain these results of stochastic entropy production for reaction diffusion process in a specific. Then I'm going to show you an example, the application example that has to do with enzyme kinetics. And then if I have time, I'll show you some other results with the stochastic thermodynamics in coarser scales. And of course, if you have questions at any time, feel free to stop me. Okay. So if we're talking about the stochastic entropy, normally one thinks entropy as a physical concept, which it is. But from this perspective, I want to try to present it from a mathematical perspective, which is also the case, right? So bear with me a little bit here. So assume you have some random variable, x, big X, that's a random variable. And its probability density, which is just a function, is given by f of x. This x is small x, right? So this is the probability density. So it could be X could be like throwing a dice, f of x would be like uniform, right? Every throw of the dice is equal at every throw. So we can also talk about f of big X. So we can put back the random variable into the function, right? There's nothing that tells us that we cannot do such a thing because the function of a random variable is also a random variable. Or even better, we can take the log minus logarithm of this function. So we have this quantity S. So what happens when we take the expectation value of this quantity? What we get is the macroscopic entropy of corresponding to this random variable. So this is also like the information, or however you want to call it. If you want to put it in the physics context, then you need to add the right unit, so you need the Boltzmann constant, but in principle, it's the same thing. So if this is the macroscopic entropy, S would be your stochastic entropy. So it means it fluctuates. So there's two big results. Well, there's many results in stochastic thermodynamics, but these maybe are two of the most important ones. And I'm going to show how to derive them in one slide. And it's really actually simple if you look at it from the mathematical perspective. So you can ask, how much entropy is produced when pushing a system from one distribution to another distribution? So the stochastic entropy production of such a movement, right? So I just told you, okay, the stochastic entropy is the minus the log of the probability distribution. So you basically just have the difference, right? You just subtract final minus initial one, and you get such a quantity that is just the ratio between the probability densities. So what is nice about this? So this, again, is a function of random variables, so we can take the expectation. And if we take the expectation of such a thing, it happens that mathematically speaking, if f1 and f2 are positive and integrate to 1, this has to always be larger than 0. And that's a mathematical identity. There's no other assumption. It just follows directly from these assumptions. So you already see that the expected value of the change of entropy is positive. It's always positive, or 0 or positive, right?
You take the expectation in the distribution F1.
Right. If you do it on F2, you get the opposite sign, right? Right. But then it's like a convention with which is your initial state and which one is your final state in some sense, right? So the entropy is positive, could also be, if you define it as negative of the other one, would also be okay, right? So in some sense, you can do it both. Now, of course, this is a very, some sense, like an abstract mathematical version. But then if you're talking more into physics, then you want to make sure that the one you choose makes sense and is consistent throughout.
Yeah, because right now you haven't even specified some sort of evolution equation. Right?
Yeah, there's nothing. It's just two distributions. Nothing. There's nothing there, right? To say, if this is the initial distribution and that's the final one, how much entropy was produced? I don't know by which method it was produced, right? I'll go there next. I don't know in which way it reached from one to the other one, right? I can also take the exponential of the minus delta S, and I get that the expected value of that is equal to 1. So in summary, I came up with two fluctuation theorems. Then the change of entropy of a system always grows, and then the expected value of the exponential of this quantity is always equal to 1. So this one is just basically what corresponds to the second law of thermodynamics, and this one, I believe it's I always forget the names, but I think it's the Crookes fluctuation theorem. So then, if you put instead of delta S the work and the free energy, you get the Jarzynski equality. So these are results from yes.
Does that mean you always have no matter what the dynamics are, or it's very stable?
Yeah, or it's 0, or you always get.
Okay.
And that's actually true.
But for example, I take my first distribution, I just take standard dice, equal distribution between 1 and 6. Then as the second one, I take a distribution which is just the outcome is always 1, which is not really stochastic anymore, but just deterministic. This has a lower entropy, I would say, because it's deterministic. But then moving from F1 to F2 would still, according to your theorem, increase the entropy, even though I go from stochastic to deterministic.
I would like to really think on it carefully what you're saying, and then see with respect to which F you're taking the distribution, and what we mean by pushing the system from one distribution to the other one, right? Which you say, okay, moving the system, perhaps there's no such thing as the absolute entropy, right? It's there's only the delta entropy, right? So what do you mean when one system has more entropy? It's just in comparison to other one, right? So then you have the delta S what grows, right? If you move it from one to the other one, the delta S will grow with respect to the initial one, right? So with respect to F1 in this case.
You cannot fix a deterministic state, I think, if you define your entropy as with an expectation value, right? Because you're always averaging over.
But the average of the deterministic thing is just the thing itself.
Yes.
Okay, yeah.
Well, I'm sure we can make it consistent, so maybe we can discuss it later. But it's an interesting question.
Because there's also a difference. Change in stochastic entropy, which is not the same as the change in the entropy, which is the expectation of S, right? Which you showed on the previous slide.
So I'm not sure if I follow you. So
right, so the change in that expectation that you have here now, right? No,
the change in this one.
Yeah. So if you go from F1 to F2,
right,
it's different from the expectation that you're showing here.
Yes, this is.
Right, because the change in this expectation, right? If that is sort of the more commonly known entropy, that is the integral of F1 log F1 minus integral F2 log F2.
I'm not sure I understand the question. So you are saying the difference between these.
I'm just thinking if there's some confusion because so this right, so the expectation of S here.
Expectation of S here. Okay, this guy.
Entropy.
Uh-huh.
Right, but the change in entropy that you're showing on the next slide is not a change in this macroscopic entropy, but it's a change in the stochastic entropy.
Right. Yes.
I think some of the confusion regarding also question from Christian is because you are trying to explain in a very simple setting where you have no dynamic.
Yes.
So you only define f of x, so x is one variable, but actually all of the stochastic thermodynamic based on x is a stochastic processes. So entropy, the stochastic entropy is a function of the
so this is a bit the point. So it's connected. So in some sense, you can write all these things in different things. The question is, what is your probability space, right? And if your probability space has dynamics, then it's more intuitive to do it in some sense, right? Which I'll do it in the next slide. But in some sense, these identities are true as just as a mathematical context, right? So this is true just as a mathematical derivation, right? And then you get some inequality that is true for that setup, right? But you can change the space and then come up with something different. Not sure if that kind of makes sense.
I was thinking that the example that you were mentioning, I can imagine that it would result in a negative value, right? The difference in this expectation, but not for the expectation as you presented on the next slide.
Okay,
which is by construction non-negative.
Right.
I think also the difference is that you're not taking the difference of the entropy, you're taking the expectation value with respect to your first
exactly
probability distribution of the difference.
Exactly.
Right.
So the difference can be negative. I think in your example, the difference of the entropies is different. But the expectation value with respect to the first distribution of the difference is not.
Well, we can also talk a bit about it later. So I don't want to stay here too long. Okay, so maybe with dynamics is going to be also a bit more clear, right? So now I'm getting from an abstract setting, right? Consider systems that has two states. For instance, it could be a Brownian particle that has two locations in space, right? So these locations are given by A and B, and you have some trajectory, a specific trajectory that moves the system between one and the other one, right? And then you say, okay, X is your trajectory, this is a big X, and this P of X is the probability of going from A to B through this specific trajectory. And P of X bar will be your reverse trajectory exactly, and say this is the probability of taking the reverse trajectory of this system, right? So in this case, we'll say, okay, the stochastic entropy production is the difference between the probability of the forward trajectory and the backward trajectory. So you want to kind of quantify the reversibility of the process. That is what a stochastic entropy does. So why is that the case? Okay, if these two are equal, then of course the delta S is 0, right? And if you think about detail balance, this is exactly what you happen, right? Like if you have a detail balance system in detail balance talking maybe about chemical reactions, the probability of going back with the flux in one direction completely balances the flux in the opposite direction, right? And then you have equilibrium. So basically, entropy production is a way of quantifying non-equilibrium and irreversibility of your system. So that is what this quantity now does. So we can do the same things that we did before with this quantity, but now we're in a different space because now we actually have a process. So maybe it's easier to understand. And with this in mind, I can jump to what this entropy.
Sorry, Mauricio.
Yeah, sure.
Normally we quantify that using detailed balance, not necessarily just the entropy, right?
Right.
So,
but in some sense, it is connected, right? Because if px equals to px bar, it means that the detail balance is satisfied, right?
No, because detail balance is the probability of being in the state times the probability of transitioning.
But that's exactly what the probability of x is, right? The probability is the probability of the trajectory x of t. So that is the probability of being at A times the probability of going through that specific trajectory all the way to B. And then backward.
Yeah, that's the possibility of but it doesn't include the probability of being in state A.
It does include the probability of being in state A.
Right, because this is just the probability of the trajectory of going from A to B.
No, right. That's okay. So maybe what I mean by the probability of x, I mean the probability of being at A times the probability of taking this path from A to B.
That's what I mean. Thank you. Okay, then I get it.
It is included there.
Okay. Thank you.
Actually, I think you'll see it in the next slide because I do it explicitly. Okay, so let me try to show you like for reaction diffusion process. So now I'm telling you about reaction diffusion. So how does a trajectory of a reaction diffusion process looks like, right? So we're talking about the particle level, and you will have some reactions happening during that trajectory. So you have a period of time, and some reactions happen. These, let's say, L reactions in a specific trajectory. So then, to understand what the reaction diffusion process does, I looked at the time intervals between those reactions, and in between those reactions, there will be diffusion. So this is a bit like what I'm drawing here, right? So let's say I have a reaction diffusion process with one species, right? So maybe you start with 5 particles. They diffuse until the first reaction happens. When the first reaction happens at T1, then maybe this one becomes 2 particles, right? By this reaction. I'm still at T1 because the reactions happen instantaneously. And then I diffuse until the next reaction. So if I have a full resolution of the trajectory of the reaction diffusion process, this is how it looks like. So something like this, right? Diffusion, reaction, diffusion, reaction, diffusion, reaction. The times are not fixed, right? The times are whenever the reaction happens. But I know it. So I can write it in terms of such a thing, right? So this has to be all these x's with a number of particles. So something important, the number of particles of the system changes, so it's not constant. I have which reaction happens, the index of the reactants, the index of the products, and the time intervals between the reactions. Okay, so it's not important this notation, just that you understand that it's a reaction diffusion trajectory. So how does the trajectory of let's say of the forward probability of such a project looks like? So you have the probability of being at the initial state. That's what you were talking about, Jay. Then
yes,
the probability, yes.
Yeah, I said yes. That was what I was talking about. Sorry.
So that's the probability of the initial state. Then the probability of diffusion on a specific trajectory. This is given by the action of something called the Onsager-Marshall path integral, which I'm not going to go into it, but let's say it's a way of quantifying the probability of a specific diffusion trajectory. Then the reaction rate corresponding to the reaction that occurred. So this is lambda nu I. So it has to do with the nu I, the reaction nu I, And it has to do with the location of the reactants and the locations of the products. So if you think in a simple model, it will be, if they're close enough, it will be a constant, and that's it. So simple enough. So basically, this gives you the probability of being initial state times the probability of all the process that's happening in between. And then for the backward, well, the same thing, right? Like the probability of being in your final state, and basically all the backward process happening, right? The diffusion of the reverse trajectory and the reaction rate of the reverse reaction that's happening. So we have a way of writing these two things somewhat explicitly. So yes.
So you do not specify a certain time at which this end state X happens.
Yeah, I mean, I do. So the times are fixed. I know the trajectory. Let's say I know what the trajectory is, right? And I know when the reactions are happening. So I know these times.
Okay, but isn't your probability, isn't this also dependent on having all different time intervals?
Yes. So if you come up with like let's say a realization of the process, your times are gonna be, let's say in a time from 0 to t. You don't even know how many reactions are gonna happen this time.
No.
So it's very tricky, right?
Mm-hmm.
So you cannot really do such a thing. So I say like this is for a specific trajectory. I'm gonna cover what you say in the very last part of the talk if I get there.
So what is then the probabilistic part in your analysis here? And then because you say that your times are fixed, that's now deterministic, not fixed.
Right.
What is the random part then?
So you can see, for instance, so say you have snapshots of your system, right?
Yeah.
And although you have the snapshots of where the reactions happen, so you already know for this trajectory, that's the case, right? Then you can calculate numerically. So you do a realization, right? When you do a realization numerically, you know when the reactions happen.
Yeah.
So you can calculate this, right? You can calculate the lambda, you can get like a value, and I show you, I do it later. And so you can calculate it numerically. That is what it's useful, right? And each realization will have a different one.
Yeah.
And then you can average, right?
Yeah, I have a question related to this point. So basically, by writing this equation with a capital L index, you mean that you fix the total amount of time you run the simulation, and then you can discretize that time.
No. So I do that in the last part. So what I say now is, I know the trajectory. I imagine that you know what the trajectory is. You run a simulation of a reaction diffusion process. You know the total time, and you know the time of the reactions, right?
Yeah, but how can you ensure that the backward process visits the same set of state like in the forward one? The forward trajectory is what you index by I0, 1, 2.
Let me show you in the next slide. So then let me say, okay, so let me take the log of these things.
Mauricio, can I ask a question? Sorry.
Sure, yes. Hi, Peter.
Question. Hi, very nice to see you. Hey, yeah, I mean, just for my understanding, so the rate of the reaction is usually events per second, which means it has units per time, right? So
right.
You probably don't have that here. You actually use a probability instead of a time-dependent quantity, right? Is that correct?
So this is a good question. So these lambda functions are reaction rate functions, so depend on the positions. I will have to take a look carefully. I think if you include the location of the products, you can think of it as a rate times a probability. But probably what you are going is that if this has units of 1/2, how come this is a probability, right?
Well, you have a problem with the product, right? Okay, but anyway, you probably have a way to deal with that. The other question that I have is about dimension of the X. I mean, if your example was that you could actually produce new particles, meaning that your X space is increasing, right?
Right.
It's usually
or decreasing also.
Decreasing or increasing. I mean,
it depends the reactions that you have.
Is that in this formalism? Because it sounds a bit tricky, right?
It is. So this is the part that is also very tricky. The system is a system with variable number of particles. Exactly. So it means that your phase space is kind of a collection between continuous and discrete spaces, right? The discrete part is the number of particles, and the continuous is the space where they move. So for instance, you have one particle, it will be R3, but you have two particles, it will be R6. So then you have kind of the phase space is the union of all these spaces.
Yeah, but I mean, okay. So in this reaction rate, there must also be a function that actually does this cloning or killing, right? It's like a birth-death process or something like that.
It is. So these lambda functions can be expressed in terms of creation and annihilation operators.
Okay, yeah.
Well, I didn't want to go all the way there.
Oh no, okay, but then it's clear. Okay, thanks.
Yeah.
Thank you. Go ahead. I mean, you can continue, right? Thanks.
Okay, so there is this part that I can separate it into the different terms. So it's just a logarithm, so I can separate it into some. So what is nice is I can separate it into the entropy that has to do with the diffusion part, the entropy production that has to do with the reaction part, and the change of entropy regarding the initial and final states of the system.
This Onsager-Markov action, is it time reversal symmetric or not?
It's a tricky thing. So the Onsager-Markov integral, to make it time reversible, you have to choose a specific stochastic integration. That is, I think it's Tratanovich that you have to choose, or I have it written somewhere. We can check it later if you want. But it's not a trivial question, and that's why I usually in this I have it proportional to, not equal, because this Onsager-Markov integral, you need the normalization factors, and these are a problem. But then if you divide them, they cancel out. Yeah. But anyway, we can split it into the three parts, which is nice. So we have the diffusion, the part with the diffusion, the part with the reaction, and the part with the initial and final states. So you can think of this, the diffusion, the reaction had to do with a specific trajectory that the process takes, right? So it means this entropy produced in this trajectory has to do with the heat dissipated by the system in this specific trajectory. And the second part has to do with the overall change of entropy between the initial and the final state of the system. Okay, so if let's simplify, we want to keep it simple. So we say, okay, this diffusion is a bit complicated. So can we get rid of it? So if we assume a simple dynamics for the diffusion over Planck-Chaban dynamics or standard Brownian motion, where your mu is 0, so there's no drift, no potential. It happens that we can express it in this way, and then this would actually be 0. So we can forget a little bit for now for the diffusion. If you have some more complex dynamics, you have to put it in, right? So that's that part. So we're left with these two parts, right? The one with the reaction, the one with the initial and final states, and we have the steady state. We can rewrite it in this way. So why is this useful to put in steady state? Because you can really see the detailed balance condition. If the top is equal to the bottom, you have the detailed balance condition from chemical reactions. So again, equilibrium. And if it's not equal, then you have a non-equilibrium system. And we can calculate this numerically. Yes?
But actually, in the first part, in the diffusion part, if you don't have the chemical potential, like if you have a system which breaks the detailed balance, then you also can have non-zero entropy production in the first part.
Yeah.
Right?
Yeah.
So this is just actual assumption that you want to get rid of the diffusion part.
Yes. To simplify, yes. But in principle, you have to put it there. Yeah. And you had asked a question before that I told you I was going to answer, but I forget what it was.
No, just to remark about Christian, because you can think about your reaction diffusion system you simulated by Gillespie, right? And then
let's go to the next part. Okay, so now to make it a bit more concrete, let me show you a simple example that has to do with enzyme kinetics. First, I'm going to introduce it a little bit to show you why I find it interesting. So consider this system of enzyme kinetics, right? You have some kind of substrate that react with an enzyme. Then it produces some complex that can transform into a B complex, and then dissociate and produce a B, right? And all of this is reversible. Whatever happens forward can happen on the backward direction. So let's say that we keep the concentration of A and B constant. So we just have a chemical kinetics for one enzyme, basically, and it can be look like this. It's a loop, right? Goes from E to AE to B, and it comes back to being just E. The difference here is that this rate K1 hat, now we only have K1 here, right? Where K1 is like a pseudo first order rate constant that has K1 hat CA. So this is the system. So now we just look at this kind of loop system of the one enzyme, right? So let's look at the entropy production one cycle. As one cycle starts and begins in the same state. We don't have to worry about the initial and final state, assuming we're in steady state. It means that this entropy production that I derive is just the rates of the forward cycle. So the rates going in the clockwise direction, K1, K2, K3, divided by the rates going in the backward direction. That's K minus 1, K minus 2, K minus 3. So you have this condition. So if this entropy production is 0, it means basically that these rates are 1, which actually is another way of writing detailed balance for the system. So one can show that this equation implies detailed balance. So we have equilibrium. So what does it say? Like, unless you really carefully pick your rates and your concentrations, in general, the system is going to be a non-equilibrium system and is going to reach a non-equilibrium steady state. And what does that look like, right? If you have detailed balance here, it means that the flux from E to AE balances out. The flux between AE and B also balances out. So everything is very fixed, right? How does it look to have a non-equilibrium steady state? Well, you have a net flux from E to AE, but that flux is the same than the AE to BE and the same to BE. So basically you have a loop, right? You have a circuit. So this enzyme acts a bit like an engine consuming E and producing B, right? That would be the idea. So it is a very simple system, but also very rich in context in the things that you can express from the physics perspective. So this is also what I mean by the qualitative understanding. So if we look at this here, this has this K1 without the hat. So it means that it actually need to, if you want, you can express it here in terms of the CA. So we can separate it like this, right? And so let's just run a simulation of this system, but now with some spatial resolution. So what do? We set up these constants to be 1, so equal to each other. So this ratio is 1, so this term will be 0. So we know that the only entropy production comes from the difference in concentrations. So if CA equals C1, CB, this is also going to be 0, you are in equilibrium. Okay? Now we move with some space dependence. Let's just start with a one-dimensional domain. We call it X. And we have one single enzyme following Brownell motion in this domain with periodic boundary conditions. And to introduce the space also in the concentrations, we say, okay, now we have a fixed but non-uniform concentration gradient for A and B, CA and CB of the system, but their integral is equal. So their integral over the space domain is the same. So we're saying in this space domain, its average value is the same. So there's reasons why I'm doing this. Let me just explain you a bit the results here. So how do I actually do the computation? So I choose these functions for the gradient of the A and the B concentration. So it's basically the same function for the A and the B, but just displaced in space by 1/2. And this has periodic boundary conditions, so it just goes around. And then if I do a trajectory, I can run a trajectory of the enzyme. And here I just color it according to its current state. So blue is just the enzyme, the A complex and the B complex in red and yellow. And I can show it unwrapped in space, like to not be confusing with the periodic boundary conditions. It looks like this. And in a dashed line, I'm showing the entropy production associated to this trajectory, the cumulative entropy produced through this trajectory. So sometimes goes down, sometimes goes up, but in general has like an upward trend.
So entropy production here is coming only from the movement because there are no reactions.
There are reactions, right?
But you just say, but you're talking about single enzyme doing, and what you're showing, this blue line is just a single enzyme moving around.
Right, but the enzyme changes state, right? It goes from E to AE to BE to E. So there's reactions, right?
host is visible in your plot. And if you go to the next slide, so in this middle, in this figure, I mean, how do I?
So okay, this is time, right, on the bottom, and on the y-axis is the unwrapped position. Unwrapped because it's a periodic domain, right? So you have your enzyme, it's blue, right? It's in this single state. It's moving around, but it can react depending on this CAB with the rate K1, right? With K1 hat, it depends on the concentration. It can react and then becomes yellow, or sorry, becomes red.
Yes.
And then it can react. It can also, with some rate, become
maybe
yellow.
Just too far away from your figure too.
So I mean, this is switching color.
Oh, you're not. Okay, sorry. Yeah, I was just.
So the switching color is the change of state of the enzyme.
Sorry, now I understand your figure.
Don't worry.
That makes more sense.
And CA and CB you keep fixed.
Right now, CA and CB is this concentration that is fixed. So what they do basically, they create a space-dependent rate. So this K1 depends on CA, right? But then the CA depends on space. So your rate depends on where the enzyme is located. So it's the very first simple approach. Then if we plot the distributions of the enzyme condition under state, we get this curve. So then the enzyme in the A complex matches kind of the A profile, the B matches the B profile. But something interesting than the blue one, you get some kind of a weak bistability between these two crossing points, right? And these crossing points is where CA equals CB. So it's some sense close to equilibrium somehow, right? So the enzyme kind of in the single state likes to be there. So that's interesting. Moreover, if I plot the average value of this entropy production for a lot of simulations, so here basically this is just this dashed line corresponds to one of these lines in this plot. If you plot the average of that, you have an upward trend, which basically tells you the entropy production in average is always positive. And then you also can do the same with exponential fluctuation theorem. So it's showing the two fluctuation theorems are consistent with this model. But there is a punchline with this. I told you that the average value of CA or CB over the spatial domain is the same. So if we were just not going to look at the spatial resolution, this would be zero. There wouldn't be entropy production and you're at the equilibrium regime. So the punchline here is it is enough to incorporate space, to look at the space a bit more closely, to start observing non-equilibrium phenomena. If you cross-grain out and you just look, well-mixed situation, I don't care about the space, maybe you'll see equilibrium. But actually, if you zoom in, this might not be the case. So this I find interesting, and maybe perhaps the point to think about it, maybe a bit obvious, but it's still interesting to see it in such a simple model.
So
Sorry. Can you just tell me something? So by non-equilibrium, you just mean entropy is being produced?
Yes.
Okay, right. Okay. Yeah, because normally when people talk about non-equilibrium states and stuff like this, it's more like active. It's slightly different. Everything produces entropy. Much.
Right. So I mean, but what you can see is that if the enzyme is around the center, it's an enzyme producing A's. But if it moves around the origin, then it becomes an enzyme producing B's. Right. So it's a bit of a give and take situation. But what it tells you is like, okay, if I modify the concentration profile of A and B's, I can effectively create a system that is producing A's or B's, depending on what you want to produce, right? So in some sense, it gives you a way of controlling this little engine that is the single enzyme kinetics. Yeah, okay.
Yeah, thanks.
Yes, so I was a bit confused at the start. Where does the non-equilibrium nature come from? Because I thought it was related to the cyclicity of the reactions, because that sort of undermines detailed balance.
Right.
But, so I think actually that has nothing to do with the non-equilibrium nature, and it's all about the homogeneous nature of these enzymes. Is that correct?
I'm not sure what you mean by this non-homogeneous nature of these enzymes. Maybe Tomás has something to say.
I think that somehow, like,
these A and B do not stay in that position if you like leave them diffuse in some way. So there is probably some non-equilibrium into like fixing A and B in this precise distribution.
Right. I mean, so you need an outside forcing to have this concentration being fixed, right? So that's where the energy is coming from. I'm not sure if that was your question.
The information that you also thought you have this reaction process which is cyclical, and that's also something interesting thermodynamically, because it means you could have a constant state of chemical concentrations without having lethal balance, because it can just go in cycles. But that's not the thing that really takes your state out of equilibrium. That's what I.
Not sure I fully understand you, but like what I can tell you, for instance, in this case, you have the K1, right? And the K1 depends on the concentrations. So if you are close to the origin, this system will loop forward, right? And if you are close to 1 or 0, this system will loop the other way around, because then your K1 is larger than your K minus 3, or the other way around, right? So what it does create is it's a bit this weird, it's the edge case, right? That it's really like in average kind of uniform, but in some parts of space it's creating something, and some parts of space creating the other one. But it balances out in the end. Yeah. But it's still a non-equilibrium state. And if you just move a little bit the concentrations out of there, then you really have a very clear non-equilibrium. Right?
Felix, these rates that you draw in that triangle are like hiddenly proportional also to the numbers of A and B, because you're forgetting A and B by calling it these three steps.
Right, and that's the CA and CB that is in the rates.
Break the condition to the one, I think, locally only.
It could be.
The entropy production is not just positive; it's also on average increasing.
Right, that's the entropy production rate.
Yes, positive. So this means that for T to infinity, I go to infinite entropy, whatever that.
In this system, and in this specific context, yes.
If you maintain your system in an inhomogeneous state as it's going this concentration, then you will always keep them dissipating. You can never get to zero.
Yeah, but to do that, you will need infinite energy to keep it running too, right?
Yeah. Okay.
And then you will produce it. Okay, it is just it's always running, right? But you cannot have something always running. Just at some point, right?
So that's the middle lower figure, right? So
right.
Average of the production is positive. Basic. How about spread? Is that a quantity of interest?
Yes, sure. I mean, I wouldn't know what to make of it right now, but it is. I don't think it's so well. I mean, maybe Tuan knows more.
But you have also the action. You can compute on the higher moment of the entropy in principle.
In principle, I mean, I have the data. I can compute it here. But I'm not sure. I'm sure there's some relevance to it, right? I will not be able to tell you on the top of my head. So I'm also trying to make sense of this, right? I'm also trying to connect how to connect these quantities to the process itself. So it is still, by the way, it's still work in progress. So it's not finished. Okay, but now it was a bit artificial to put.
Mauricio, can I?
Sorry, yes.
Question. Yeah, I was waiting for the other.
No worries.
Oh, just a follow up actually on this influence of the distributions of A and B. So if you would take a flat distribution along the position, so no spatial dependence,
right?
You could also have entropy production, right? If you take them different.
So you would have entropy production, but in average, it would be horizontal as well. So
it will be horizontal, but it will be increasing, right? It will show the same behavior.
I mean, if the two are uniform but the same, or uniform but different?
Yes.
Just to different, or just to
different values. So one could be.
Yes, you have it. So if you so this is here, right? This still in the well mixed case.
Yeah.
Then if you see and CB are different,
I understand. But your big conclusion would be, I mean, if I interpreted this right, that even if CA and CB on average are the same,
right?
Because they are not spatially different, right? you still have entropy production.
Right.
That is actually the
Yes,
very
that's the
interesting
punchline.
conclusion, right?
Yeah.
Okay, thank you. Okay,
Yeah, exactly.
yeah, great, thanks.
Okay, so it was a bit artificial to introduce this C and CB like as a concentration. So why don't we put it as particles? So again, we're in one dimension. So let's say that your enzyme is blue, your A is a red particle, and your blue and your yellow is a B, right? So how this works is like what I showed you before. If E and A are close enough, for instance, then some reaction radius sigma, then it can react with the corresponding rate, and it becomes an AE. Then there's a question where you should put the complex. Well, you think that these reaction diffusion processes are modeling some actual physical, molecular, or more like a DFT or whatever you want to call it. So there is some form of attractive force between the things that bring them together, right? So you say, okay, let's put them in the middle point between their original positions. So we put it there. Then this can react again, become the complex, and then this complex can separate. And then again, to keep detailed balance, we have to put them distance sigma apart of each other. So this algorithm is what is basically used in reaction diffusion simulations, and it can show that it satisfies detailed balance at the local level, because everything that happens in the forward direction can happen on the backward direction as well. So we do this now, and instead of using these fixed concentrations, now we put the particles themselves, and what we do to create the spatial non-homogeneity is we have death of particles in birth of particles in the center, of the A particles higher, and then killing of the A particles in the outer origin, and the other way around for the B particles. And all this process is reversible, but with different rates. So we do that. We essentially get the same results as before. So we get something that looks very similar than this, but with one more thing. If we plot simulations for different reactive radius, and we plot the relative change in the diffusion constant of the system, we see an increase of the diffusion of the enzyme. And experimentally, people always talk about enhanced enzyme diffusion and where it comes from. So I'm not saying that this is the reason, but it's a hypothesis that could be interesting to check. That in the end, this kind of artificial part that you do in the reaction diffusion process, that you put the molecule somewhere in between, is kind of making the enzyme move faster, right? And that's increasing the diffusion coefficient of the enzyme. So now looking back at it, it's a bit obvious that this happens, but in some sense, it also represents something that actually might be happening at the physical level. So it is possible that the enhanced enzyme diffusion, it is a consequence of having bimolecular reactions in the enzyme cycle. So I mean, what else? So let's just for fun, where I do like a more exaggerated simulation, where it's 3D. I put this the same single enzyme kinetics, and let's say here, okay, the enzymes in their single state are yellow, the A particles are blue, and I show you 4 snapshots of the simulation, right? In the center, you have A particles being created, and then they die uniformly in space. So this is not the best example because not everything is reversible. So, but I just want to show you something that I mean, I haven't got the chance to prove with a more sophisticated model. But what happens, right? So in this case, now I'm going to put the rates for the forward reaction to be higher than for the backward. So it will mean that the reaction with the A particles is favored. And what does that do? So what happens is that now the distribution of enzymes goes to the center. So this also makes sense, right? If you have this reaction diffusion process that like reactions happen and brings the enzyme closer in the middle point between the reactant and the enzyme, if you have a concentration gradient fixed in the origin, you would effectively have a drift of the enzymes towards the origin of the system. So this is another part of the non-equilibrium process, right? If you have non-equilibrium, so you're keeping the concentration gradient of A and Bs, then you are going to observe a drift going towards the favored particle of the favored reaction, let it be A in this case, right? So it will go towards the location where the A's are. So you have an effective drift of the for the enzyme. So it's not only an enhanced diffusion, there's also a drift that is occurring through the non-equilibrium process. So this is a bit the second punchline, right? You can have drift produced and driven by the non-equilibrium process of the enzyme. So that's the third part over. So I have another part, but how are we doing on time? Should I go for it or?
Mauricio, can I ask a question?
Okay, sure. Ask me, Peter.
Yeah. So you said that these enzymes drift to the center,
right?
And that's because there the A and the B particles are located, or the A
right.
particle. But what makes this A particle go to the center? Is that some sort of an external field or something? Or
no? So there's no potentials. That's the interesting part. There's no interaction potentials. There's just the reaction mechanism that I'm explaining here. So if the enzyme is here and the A particle is there, when the reaction happens, the complex enzyme is placed in the middle location, right? So that effectively kind of gave a little jump to the enzyme forward.
Yeah, but why do they go to the middle of the box? I mean, this could be random all over the box, right? So why is this located towards?
Yeah, I mean, so in some sense, this is of course a modeling choice, but you would assume that why would be the middle point? I mean, this is one dimension, right? So it could be just along the line. So why the middle point? In some sense, when you are thinking of this actually happening in a physical system, when the reaction happens, in some sense, you are modeling there is some interaction potential, right, between these two things, and when they react, they would come very fast close together, right?
Yeah. Okay. No,
I mean,
but
I guess you have better intuition for
this
this.
Displacement. So this is the origin of the jump.
Yeah, it is
the enzyme. But I didn't understand why it would go to the middle of the box. I mean, this is between the two molecules. But if you do this randomly all over the box, it would just uniformly spread, right? So what is the reason that it actually goes to the center?
So I'm not sure. Okay, so first, so this is just X is your domain, right?
Yeah. So, but you have this three-dimensional box, right? So maybe.
No. Okay, so in this case, right now it's just one-dimensional, right? But you are talking about this case now.
Yeah, this case, yes, exactly. So you do have something special in the center, right? You say something that A only occurs in the origin. So what is the reason for that?
Why right. So I mean, this could be like an external contact with a reservoir, or like
okay. So you do have an external. Yeah, you do have an external influence where you only.
Yes. Of course, yes.
I said, okay, I didn't get that.
Yes.
Okay, so
yeah, that's the one driving the non-equilibrium in the end, right?
Makes sense then. Okay, thank you.
Yeah. So not super long, but it's a bit heavy, so I'm not sure I want to kill you guys. Maybe questions? I mean, I can give you like a little bit of. I can maybe just tell you about what it's about. Yeah, I can gloss over that. So you were asking at some point about the Pedro was asking about the phase space of the system, right? So if you have one Brownian particle, you have a stochastic differential equation, and you have an equation for its probability distribution. This is a deterministic PDE, right? And the phase space of your system is just something simple like this. So it's just R3, for instance, right? So you can say that, okay, you can show that if you run many of these trajectories, they satisfy the probability density given by this equation. And here are, for instance, some histograms of all these trajectories and the solution of this PDE, how they match. So for every stochastic process, you always have some evolution of the probability density. The tricky part, of course, if you have a reaction diffusion process, the number of particles of your system changes. So your phase space is a complex thing, right? It's like this will be for one particle, but then you can jump to the 2-particle part of the phase space, and you can jump to the 3-particle part of the phase space, and so on. So your probability density is more complex. So you have it's going to be this rho n, That is the probability of having n particles at these positions xn for every possible n of your system, right? So I'm not going to go into detail with this, but this is the paper that I have with Tommaso and Wout that had to do with writing reaction diffusion process in terms of in quantum spiral formulations. But the idea is you encode all these probabilities in some ket row. Xn would be the state of your particles at xn, and the connection between those two is given by such an equation. And then we can write a master equation for this thing. We've done some generator H. We use H just in analogy to quantum mechanics, but it's not a Hamiltonian. And this H is given by the diffusion operators and the reaction operators, or something like this. So the beauty of having this formulation, so I don't want to go into detail about how we get this master equation, but the beauty of having this formulation, we have this generator, so we can calculate the propagator of this thing as exponential of this H. So let's say now, instead of having the full resolution trajectory, we have snapshots of fixed time steps. Like an experiment, we use every time step, we look at the experiment and we see so many particles at such positions. So how do we calculate the probability of a forward trajectory of that system? So between two states, we don't know if the system, let's say the one state has 5 particles and the final state has 5 particles. We don't know if the system just diffused or just diffused, created one particle, annihilated one particle, and diffused and arrived at that point, or maybe created 2 particles or 3 particles that killed 3 particles and went back to that point. We don't know which path it took, but the propagator knows. So this e to the th knows. It takes all the possible paths in some sense. So it's a coarser description, but at least we can compute something. So we can compute these trajectories as before, but now for these snapshots. Initial probability, we have that the state x0 is propagated in some direction with the final state x1, and so on. We keep doing this in every snapshot so we can get the full trajectory. And then we can do the same for the reverse one. And lucky enough, we can again separate it between the diffusion contribution, the reaction contribution, and the initial and final state contribution. The idea of this, I mean, it's not, I haven't applied this to anything, but in principle, you can apply it to a different kind of observations. In a numerical simulation, you have all the information, perhaps. But an experiment, maybe you just have snapshots every time step. So then you can apply the same methodology with this. Yeah.
And it just gives you the lower bound of the true entropy
Right.
reduction.
Exactly. Because it's coarser, right? So it won't be as precise as the other one, but at least there's something you can calculate. Exactly. And the beauty of this is also it shows a consistency across scales. So we take the expected value of this, we recover the results from the macroscopic theory. But these R's can also be written in terms of the macroscopic reaction rates. So we really produce a connection between the micro all the way to the macro. But anyway, work in progress, as I said, and I won't kill you anymore. So, summary and remarks. I show you an intuitive derivation of stochastic entropy, perhaps a bit controversial, and derive it for full reaction diffusion processes. For enzyme kinetics, I reviewed the well-mix case. I show that just incorporating in better resolution can yield non-equilibrium states. I show you that enhanced enzyme diffusion can be a consequence of biomolecular reactions, but more importantly, that there can be a drift driven by chemical paths that is causing that causes this drift. The question is also what's the relation with entropy production in a more precise way? I don't know. And then at this more stochastic entropy with a CG resolution, where your time resolution is more coarse-grained. So, of course, I present this in the context of biochemical process, but this is very robust scheme, so it can be also used for agent-based systems, right? So if you're talking about social systems, anything that can be described in this reaction diffusion context, you can apply the same things. This framework is quite general at the mathematical level. So it would be interesting to see, I don't know, what's the entropy production of your opinion dynamics network, right? That's also an interesting thing. And maybe you start seeing all these cycles of opinions too, and there's like some kind of non-equilibrium phenomena. Who knows? Okay, with that, I thank my collaborators, Artemi and Suzuki. Also, Hong is my PhD advisor for a long time, which a lot of these ideas come all the way back from him. So I'm happy I can work with them now. The paper is not published, as I mentioned, so hopefully it will be at some point in the May or so. The paper, if you are more interested in this kind of field here in quantum methods, we have the paper published about that now in Review of Modern Physics that is coming. It's coming out soon, hopefully, but it's already in the press. I mean, it will come out, and then some other reference that you might find interesting. But thanks.
Hey, Mauricio, can I ask you a quick question?
Yeah, sure.
Yeah, so it's about your measure of entropy. So yeah, basically what you have there is a measure of detailed balance, right? Because yeah, if you get this thing to be positive and growing, that means detailed balance is somehow broken. That's why you use the word non-equilibrium, right?
Right. Yeah.
But normally the theorems in statistical physics of detailed balance or the definitions, they use, difference in free energy and the work done over trajectories, etc. While you sort of bypassed all of that by just, giving us that definition, as you call it, stochastic entropy. I'm just wondering, I mean, can you write that thing in terms of the traditional thing, which is differences in free energy and the work done over trajectories?
Yeah, so I haven't done it for the system, but I mean, this is how the community in stochastic thermodynamics approaches this problem. They always see it from a physics perspective, which it's also fine. But I guess what I really want to show with presenting in this way is that it is more general than the physics perspective. It's really a consequence of probability theory, which of course, if you apply it in the context of physics, then you get like very specific things, and then you can come up with physical concepts like work and free energy and see what you can build around it. And it's a bit the same as dynamical systems, Newton's equations, right? Like in some sense, the theory is there, and then of course, if you have Newton's system, well, then you have like some conserved quantity and some more specific structure, right, that you can build upon.
Yeah, I guess what I'm trying to say is that, but maybe this is all explained, and I'm just, I just don't know enough about this. Is that if I would rewrite it in terms of physics quantities, free energy and work done, etc., this stochastic entropy wouldn't be equal to what we would call entropy in that physics context.
Yeah, so I mean,
this is what I'm confused here.
Right. So I can tell you. So this whole field of stochastic thermodynamics, that's exactly what they do. They use, in some sense, like more a physical presentation. So if you go at the papers that the people in this field work on, they write in this way. I mean, the Jarzynski inequality, basically what I have that was this exponential to the minus delta S, the expected value equal 1. They say, okay, it's not delta S, it's like is the work between 3 points and the difference in free energy and the work along a trajectory. And you can write it in terms of these quantities. So it is all in some sense the same. So yes, you can write in terms of physical quantities. And this is actually how it is normally done. So my presentation is the one that is unusual somehow.
Okay, thanks.
Can I comment on that?
Sure.
For Jay's question, there is a classical review by Van der Broek and Esposito,
right,
which start with the first law and second law of thermodynamics written in terms of work and entropy, and then he make a connection with the stochastic entropy.
Right.
So you can just.
Okay, so there's a relation between stochastic entropy and the other entropy. Is that what you mean?
Yes. I mean, that's how it's usually presented.
Yeah. Okay.
Yeah. So I mean, you can do it for a physical system, but yes.
Can I ask a question?
I had a question about the final equation you showed. So this is kind of a complicated thing, right? So if I understand correctly, like to get Crookes fluctuation theorem, for example, you would need to introduce a symmetry like microscopic reversibility, and then it simplifies into something nice, which tells you more than you knew before. Because you make a distinction between physics and mathematics. Do I understand correctly that you call it physics the moment you introduce such a symmetry that would turn this into an expression that actually tells you something non-trivial?
So I'm not sure about this. This first part of the introducing microscopic reversibility. I guess you can do that from the mathematical, but you need it, right? Like from the physical constellation, it is there, right? The microscopic reversibility is there. From the mathematical, well, you need it, otherwise you cannot say anything about reversibility, right? So then you have to have some form of reversibility. So that's the first part. Then the second part, not sure.
Yeah, well, so then I wonder a bit, like, how do I really understand this distinction you make between mathematics and physics? That's not really clear to me, because to me,
Right.
yeah, you need to make some sort of physics assumptions, and then once you specify those, then it becomes mathematics.
Right. So for instance, like in the beginning of the talk, right? So I show you somehow some mathematical identities, right? Say, okay, I have a distribution F1, a distribution F2, some random variable X, and with just that, it's like the same as 2 is bigger than 1, I get some quantity that is positive. That's it. That's a mathematical statement, right? If you want to say something about it, then you have to build a bit the narrative behind it, right? And then, but my point being, of when you put it in the mathematical context, you are not bound by your physics understanding of the system, right? So if you want to apply it to opinion dynamics, once the entropy production of such system, then if you're still thinking in physics, you're going to have a hard time. But if you just put it from the mathematical concept, then maybe you can do it easily, right? I mean, that's information theory.
You need to be know certain symmetries it has, which follow from the nature of this opinion dynamics,
right?
Which are almost like physical assumption, but then corresponding to whatever
right
symmetries you have in that case, and then
right.
Mauricio, can I ask a question?
Sure.
Yeah. Okay, very nice. So I have a question about equation 9 here. So you basically have 3 terms, right? So the production of your diffusive term, the reaction term, and the set concentration or something like that, or the beginning and the end term.
Right, yeah, exactly.
What I was wondering, so I mean, if you actually have a process that produces particles, it's kind of very logical that there is a entropy production, right? Because you're introducing more degrees of freedom, which increases the possible entropy. So where is this actually being realized? Is that now in the second term where you have this reaction?
Right, correct. So anything that has to do with the interaction with the environment, I mean, there's 2 possibilities, right? So if you think about diffusion, the interaction with the environment can be through a thermostat, right? So if the noise is not so simple, perhaps you can have some form of entropy production be introduced to the thermostat. If the noise is simple, then it will not be the case. And then for the reactions, everything is in here, right? So every time that you have a reaction that adds or removes particles or like whatever it does it through this part of the process.
Yeah. But I mean, in the beginning, you said also that it was actually the concentration of A and B, which was actually the determining thing. But when I look at this equation, it seems to be the production, say the annihilation and the creation of particles, right? Which actually make this entropy. Because the diffusion term is probably not so productive in that sense, or will
no,
be.
In this case, not. In the case that you're talking about, not.
Yeah.
So
So here, the middle
creation,
term is then
but it's not only the creation or annihilation of particles; it's also the transformation of particles into different states. So in the case of the enzyme, it's back here. Is this right? So this is still a reaction, right? It doesn't add or create a particle. I mean, you can see it, right? You can see it as eliminating an E and creating an AE. So there's what it would be.
So is it then still true that the total number of particles in the system remains constant? Is that actually?
I mean, I guess it depends how you want to think of. If you want to think of AE as a completely different thing than AE, then
so
yes,
the enzyme remains constant, right?
Yeah.
Okay. All right. Okay, I have to study this more in detail. Thank you very much. Anyway, it was a great talk. Thanks.
Glad you made it. Here, I'm keeping CA and CB constant.
Binds with AE, then I guess it's sort of replaced by another A.
Yeah, but that's controlled by your control of the reservoir in some sense, right?
Exactly.
Yeah. It's a bit of an idealized system, right? Like maybe you cannot do something like that experimentally, but you can get a lot of insight just of thinking about this setup.
Thank you. Do you think that like by adding also a monomolecular reaction, because I feel like you said that this biomolecular reaction affects this diffusion coefficient, like experiment like in the simulation, but I would say that also like linear reaction would, like, let's say that you have only A transforming into B, but B has a slower diffusion coefficient,
Sure.
and then it goes back to A.
Yeah.
You would see this also in the diffusion of A if you just
Right. Yeah.
But
See, right now I'm assuming that the enzyme has the same diffusion coefficient in the 3 states, so it's also a bit of a maybe unrealistic assumption, right? But yeah, you're right. So if you are doing your regular reactions with changing states that have different, but then what would be the diffusion coefficient of the enzyme? Maybe it's an average of 3. I don't know.
do you think that relates to like these corrections we could add to the propagator due to the reactions? Like this change in diffusion coefficient is something like a correction to the propagator due to the reactions, right? Or
yeah, right. I think because I mean, at least how it's separated initially in this equation. Right. This is just if you really know the intervals when the reactions happen, like you know that in between the interval that you're doing the diffusion, there's no reaction, and once the reaction happens, then you can use the other diffusion coefficient on the other side. But if you don't have that, the propagator it will do it. It will still do it. It will still do it. The propagator still do it, right? Because they will have different diffusion coefficients for different states. Yeah, it will still do it.
All right, Mauricio is around today, the whole day.
Yeah.
So feel free to tackle him. You have more questions, but I think we can close the session and go for lunch downstairs.
Great.
Thanks.